Welcome back into the control burst. In the previous chapter, we learned that most real control systems use a combination of feed-forward and feedback. But that naturally leads to another question. If we know we need feedback, how do we actually design the controller? There isn't just one answer. Engineers have developed many different design methods over the years, each based on a different philosophy. In this chapter, we will look at four representative approaches: PID control, LQ optimal control, H infinity control, and model predictive control, or MPC. Let's briefly review chapter 2. Feedforward acts before an error appears by anticipating what will happen. Feedback reacts after the error appears and corrects it. In practice, we usually combine both. Now, the next question becomes, how should we design the feedback controller itself? That's what this chapter is about. Imagine several engineers are given exactly the same control problem. They all want the same goal: stable, accurate, and efficient control. But each engineer may choose a completely different design philosophy. One may use PID, another may use formulate an optimization control problem, another may prioritize robustness against disturbances, and another may repeatedly predict the future. The destination is the same, but the look is different. That's why so many control methods exist. Let's start with probably the most famous controller, PID control. PID generates the control input using the current error and its history. It consists of three components. The proportional term reacts to the current error. The integral term accumulates past errors to eliminate steady-state offset. The derivative term looks at how quickly the error is changing, helping improve stability and damping. By adjusting these three gains, engineers can achieve surprisingly good performance for many principal systems. PID is simple, intuitive, and still one of the most widely used control methods in the industry today. PID focuses on tuning gains, but LQ optimal control starts from a completely different idea. Instead of asking, how should I tune the controller? It asks, what does good control actually mean? We define our objectives mathematically. For example, we may want fast response or small tracking error and low control effort. These objectives are combined into a cost function. Then, optimization is used to find the controller that minimizes that cost. Notice something important. Optimal does not mean universally best. It only means optimal for the objective that you defined. H infinity control builds on optimization but changes the design philosophy. Instead of optimizing the average performance, it prepares for the worst case. It assumes disturbances, uncertainties, and modeling errors may occur. Then, it designs a controller that minimizes the worst possible impact. This makes the controller much more robust. Of course, this robustness sometimes comes at the cost of being more conservative. So if LQ says, let's optimize expect performance, H infinity says, let's make sure the system still behaves well, even under difficult conditions. Finally, let's look at model predictive control MPC. MPC continuously predicts the future behavior of the system using a mathematical model. Then, over a finite prediction horizon, it solves an optimization problem to find the best control sequence. But here's the interesting part. Even though it computes an entire sequence, it only applies the very first control input. After that, it measures the new state, predicts again, optimizes again, and repeats. This process is called the receding horizon. Because optimization is repeated every sampling period, MPC naturally handles constraints, multiple variables, and changing environments. That's why it has become extremely popular in modern automotive and robotics applications. So let's compare these four approaches. PID is simple, intuitive, and based on the measured error. LQ optimal control defines an objective mathematically, then find the best controller for that objective. H infinity focuses on robustness, again disturbances and uncertainty. MPC predicts future behavior, repeatedly optimizes, and naturally handles constraints. None of these methods is universally better than the others. The right choice depends on the system, the design objectives, and the practical constraint. Different philosophy, different strengths. So far, we have focused on designing the controller, but controllers often need information that we cannot measure directly. For example, vehicle slip, motor torque, battery states, or many internal variables. How can we estimate something we cannot measure? That's the topic of the next chapter. We will introduce the concept of state estimation, observers, and Kalman filters. See you in next chapter. Thank you for listening.